This is the final exam review version B, Math 1050. Question 1, Unit 1, difference quotient. Going to start with the f of x plus h part of this. When you're plugging something in to a function, that term that you're plugging in this case, x plus h, replaces just the variable x. So x squared becomes x plus h squared. X plus h squared is x plus h multiplied by x plus h. You multiply those together, and then distribute the 2. Now this whole combination of terms replaces f of x plus h in the difference quotient. Then we subtract the original function f of x and divide it by h. So negative 2x squared, positive 2x squared, and this becomes a negative 5 when you distribute the minus sign. So that negative 5 cancels with positive 5. The terms that are left over in the numerator are 4xh plus 2h squared. And then if you factor out an h from the numerator, that leaves you 4x plus 2h. And then cancel the h. You're left with 4x plus 2h. For question number 2, find the inverse, also from Unit 1. We're going to, for part A, switch the place of x and y, or switch the place of x and f of x. So f of x becomes x, and x becomes y. And then we need to get y out by itself. So we got to subtract 5, divide by 3. Now to get y minus 1 all by itself, we're going to need to do a cube root on both sides. And then add 1. And always end with function notation. Part B, we're going to switch f of x and f of x, or switch the place of x and y. It's just a little shorter to write y instead of f of x. So now we're going to multiply y minus 1. We're going to multiply y minus 1 here and here. And then divide by x and add 1. Question 3. Now we're graphing a square root. And there's a horizontal transformation inside the square root. X minus 1 means it's going to move to the right. Now, it's written backwards, actually, from what may be considered a little more common. So this could also be written as f of x equals negative 3 times the square root of x minus 1 and then the plus 2 on this side. That might make it a little more clear that this plus 2 is a vertical transformation up 2 units, and the x minus 1, this is a horizontal transformation to the right 1 unit. So if we go to the right 1 and up 2, this is the starting point of the square root graph. Normally, if you recall, a square root graph points up and to the right. Now, the negative 3, the negative sign flips it upside down, and the 3 stretches it vertically, so it's going to be upside down and a little more stretched out, would look something like that. So what we need to find out now are just some exact points. And because the graph is going to be pointing to the right, we can only use x values that are to the right of this point. So x equals 2 Um, if x equals 2, 2 minus 1 is 1. Square root of 1 is 1. 1 times negative 3 is negative 3. Negative 3 plus 2 is negative 1. And one more point. Now we're going to have to take a square root, so I want perfect squares in there. So I'm going to let x equal 5. Because 5 subtract 1 is 4. Square root of 4 is 2. 2 times negative 3 is negative 6. Negative 6 plus 2 is negative 4. Our, our question 4, finding the zeros of a polynomial. This is from Unit 2 now, Chapter 2. So for part A, this is the P divided by Q, the rational zeros theorem. So the factors of P are the factors of the constant at the end of the polynomial, 16. So the factors of 16 are plus or minus 1, 2, 4, and 8, and 16. And then Q are factors of Q are factors of the leading coefficient, or leading coefficient in this case is 1. So if we divided now P divided by Q, it's going to be all of these numbers divided by 1, which since anything divided by 1 is itself, this really is just P divided by Q, this list here. So those are the possible rational zeros from the rational zeros theorem. Part B is now we need to find all the zeros of the polynomial. This is going to come from, these are going to be found using synthetic division. So I'm going to start with positive 1 and use the coefficients of P of x. It looks like that won't work. Let's try negative 1. And that's not working. Try positive 2. And I'll look there. Okay, we got one. So if x equals negative 2, then x plus 2 is a factor, and then these are the coefficients of a reduced polynomial factor. So if we start with x to the third, then the reduced polynomial is x squared. Now, once we get to a quadratic expression, we don't need to do synthetic division anymore. Remember, we can find the remaining zeros from the quadratic either by factoring, if it happens to factor. If it does not, we have to use the quadratic formula. So the quadratic formula is opposite of b plus or minus b squared minus 4 times a times c all over 2a. So the opposite of b plus or minus b squared minus 4 times a times c all over 2a. I have 9 minus 32 is negative 23 all over 2. Now square root of 23 doesn't simplify, but you take out the minus sign, remember, as an I. So the zeros are x equals negative 2 and x equals negative 3 plus or minus I square root of 23 all over 2. That's the answer to part B. Part C is our polynomial here in factored form. This says into linear, which is x plus 2 is linear, and then irreducible quadratic would be this irreducible quadratic. Question 5 is also from Unit 2. This is Chapter 2, finding now a polynomial. And it's going to be degree 4, which means we should have 4 zeros listed. So we have x equals -2 with a multiplicity of 2. So for part A, if x equals -2, then that means x plus 2 is one of the factors, and it has multiplicity 2. I'm going to write it twice. Now, we have another 0 there. If we subtract the 1 over and subtract the I, we're going to have x minus 1 minus I. Now, the one that's missing is x equals 1 minus I. Because remember, complex zeros always come in pairs by switching the sign in the middle. So 1 plus I means 1 minus I is the other 0. So if we subtract the 1 and add the I to the other side, we're going to have x minus 1 plus I. Now we need to multiply these two factors together. So x times x is x squared minus x plus ix. And now we distribute the -1. That's going to be negative x plus 1 minus I. And then we distribute the negative I here, and we're going to get minus ix plus I minus I squared. So we have opposite terms that'll cancel out. I squared, remember, is -1. So this is minus -1, which is plus 1, and then another plus 1 makes plus 2. So we have x squared, combine the negative x and negative x, negative 2x, and plus 2. And then we have x plus 2, the second power. Now, oftentimes there is a leading coefficient, a, which they have not given us. So we have a degree 4 polynomial, because this is going to give us an x squared term, and this is already next. So this is x squared times x squared, which is x to the fourth. What we don't know is the value of a, and that's why we have this other piece of information that when you plug in a 0 for x, then everything simplifies together to 8. So this side of the equation becomes 8 when all of the x values, x variables are 0. So 0 plus 2 is 2. 2 squared is 4. And then 0 squared minus 2 times 0 is 0. 0 plus 2 is 2. We have 8 is equal to 8a, therefore a equals 1. So the polynomial p of x, we can list 1 for a, but we don't necessarily need to, because 1 times anything doesn't change the value. Question 6 is also from Unit 2. This is Chapter 3, Graphing Rational Functions. So um, first thing I'm going to do is write the function f of x in factored form in numerator and denominator. So the vertical asymptotes are the domain restrictions that come from the values in the denominator. X cannot be 3 nor -3. So I'm actually going to write the domain right now. -3 is excluded, and +3 is excluded. And then that's where our vertical asymptotes are going to go. -3 and +3. Now the horizontal asymptote is comparing the degree of the numerator to the degree of the denominator. So In this case, we have degree 2 divided by degree 2. If they're the same degree, remember you divide the leading coefficients. 1 divided by 1 is 1. So the horizontal asymptote is the line y equals 1. X and y intercepts. If we're going to find the x-intercept, we're going to let y equal 0. And a fraction is only going to ever equal 0 when the numerator is equal to 0. So the two values for x that will make the numerator equal to 0 are -1 and +1. So the x-intercepts are -1 comma 0 and 1 comma 0. The y-intercept is found by plugging 0 in for all the x values. So if I plug 0 minus 1 is -1, 0 minus 9 is -9. So the y-intercept is 0 comma 1/9. So the location of those 3 points gives us a picture in the middle like that. And then as we near the vertical asymptote, we have to determine, are they both going down in the same direction or are they going in opposite directions? The vertical asymptote for x equals 3 came from this factor of x minus 3. And since it has an odd multiplicity, meaning it only appears once, then what we discussed in class is odd multiplicity for those factors that produce vertical asymptotes. It means on either side of that vertical asymptote, they're going in opposite directions. One side is going down, means the other side has to be going up. And then a similar argument can be made here. On this side of the vertical asymptote, x equals -3 came from x plus 3 as a factor. X plus 3 appears only once. Multiplicity 1 is odd. So on either side of this vertical asymptote, we're going to have opposite ends. If one side's going down, the other side has to be going up. To solve a logarithmic equation, we need to get the logarithm by itself and then use a base to cancel the logarithm. So if we divide by 2, and then use a base 3 on both sides, cancel the logarithm, and then subtract 1, we get x equals 26. For part B, we need to condense these two logarithms into one logarithm. So we condense these into a log base 9, and because there is a minus sign between the two logarithms, we're going to use the quotient rule. So x plus 6 is in the numerator and x is in the denominator. Now we can use a base 9 on both sides to cancel each logarithm. So we have x plus 6 divided by x is equal to 2. Now we don't want to solve an equation with a fraction, so let's multiply by x on both sides. Okay, question 8. We want to find out at what rate should we invest. So we're solving for R. Now, there were two different versions of compound interest given. It depends on what kind of compound interest. If it's compounded continuously, then this is PERT. So we're going to use this compound interest formula, and we're going to solve for R. That means we need to know the principal investment, which is $10,000. The future value, A, is 30,000. And then the amount of time is 10 years. So now we're solving for R. So future amount is equal to the initial amount, base E, to the unknown interest rate R, times 10 years. So divide by 10,000 on both sides. And now we use a natural log on both sides. So natural log here, because remember natural log cancels base E. So now that's just 10 times R. So divide by 10. Get the interest rate. So that's 10.98. No, it's 10.99. Graphing logarithmic function, also from Unit 3. Logarithm functions have a vertical asymptote. Vertical asymptote is a domain restriction, and it's usually here along the y-axis at x equals 0, unless the graph has been shifted horizontally, which this one has, x minus 1. Shift everything to the right 1 unit. So the vertical asymptote is at x equals 1. We need to find a couple of points on the logarithm graphs are typically on the right side of the vertical asymptote. So we need to find values greater than 1 that we can plug in. So I'm going to start with x equals 2. 2 subtract 1 is 1. Remember, log of any base of 1 is always 0. 0 plus 1 is 1. So 2 comma 1 is on the graph. Now at this point, we have to be a little more strategic on the values for x that we choose, because this is a log base 2. I want whatever comes out of this to be a power of 2, like 2 to the first power or 2 to the second power. So if I want this to equal 2, that means x has to equal 3. So 3 minus 1. 3 minus 1 is 2. Log base 2 of 2 is 1. 1 plus 1 is 2. And then the next power of 2 is 4. So if I want the whole thing to turn into 4, that means x has to be 5. 5 minus 1 is 4. Log base 2 of 4 is 2. 2 plus 1 is 3. Part A, question 10, multiplying matrices. We need to determine the number of columns for matrix A. So matrix A is a 2 by 3. And then the number of rows of matrix B. Matrix B is a 3 by 3. So because these two inside numbers match, then we can perform the multiplication. This entry is a combination of this row combined with that column. We're going to have 2, and then 2 times 1 is another 2, and then 0 times negative 2 is 0. So 2 plus 2 plus 0 is 4 here. This row in this column, so this is negative 4, negative 2, and negative 2 makes negative 8. This entry is this row to that column, so this is 1 plus negative 2 plus 0. And then this entry is bottom row middle column, so that's negative 2, negative 2, and a positive 1. Let's see, negative 2 and a positive 2 rather. So this is negative 2 plus positive 2, which is 0, and then 0 plus 1 is 1. And then we're going to have this entry is 5 plus 8 plus 0, which is 13. This entry is going to be negative 10 plus negative 8 plus 0, which is negative 18. B times A. B is a 3 by 3, and A is a 2 by 3. So since these two middle numbers don't match, B is not possible. Part C, 3 times A means every entry in matrix A is multiplied by 3. And we're going to add that to matrix C. And matrices can only be added together, remember, if they are the exact same size. So these two matrices are the same size. We're just going to add the entries in the corresponding spots. Question 11, partial fraction decompositions from Unit 4. Since there are two factors in the denominator, this is going to have two partial fractions. Now, if we multiply both sides by the lowest common denominator, but now we need to solve for a and b, but we only have one equation. So remember, we need to cancel a to solve for b, and then to solve for b, we need to cancel a. So let's cancel a by multiplying it by 0. So if x is -1, that's going to be a 0 right here. Now let's let x equal -1. Negative, the opposite of -1 is 1. 1 plus 8 is 9. -1 plus 1 is 0. -1 minus 2 is -3 times a is, or times b is -3b. So divide by -3, b equals -3. If we want x to be 2 now, now that's going to cancel b and allow us to solve for a. So opposite of 2 is -2 plus 8 is 6. 2 plus 1 is 3. 3 times a is 3a. 2 minus 2 is 0, so b is canceled. So divide by 3, a is equal to 2. So the partial fractions are 2 over x minus 2 plus -3 over x plus 1. Okay, question 12, we're stacking logs one row at a time. So the bottom row has 48, then 45, then 42. So looks like each row has 3 less. So this is an arithmetic series. It's 48 plus 45 plus 42. The final row has 24 logs. So this is a partial sum of an arithmetic sequence. The formula for that is n divided by 2 plus the first term and the last term. So we know that the first term a sub 1 is 48, the last term a sub n um, is 24. The bottom row has 48 logs, the top row has, or for the final row has 24 logs. What we don't know is how many terms this is, n. This is an arithmetic series, so we can create an explicit formula. So the explicit formula of an arithmetic sequence is first term times n minus 1 times the common difference d. The common difference d is -3 because we're going down by 3 every time. So first term is 48 plus n minus 1 times -3. So if that -3 is distributed, we have -3n plus 3. So now we need to figure out the n value for this final term, 24. So 24, we go in place of a sub n. And then if we solve for n, that'll tell us what spot that's in. So 24 in place of a sub n. So if we subtract 51 on both sides, that is -27. Divided by -3, n equals 9. So there's 9 rows of logs. So 9 divided by 2. 9 divided by 2. Remember, n stands for the total number of terms. So that's 9 divided by 2, multiplied by the first term, 48, plus the last term, 24. So the sum of those 9 terms is 324. total logs in those 9 stacks, or 9 rows rather. Question 13, this is back from Unit 4, solving a system of equations using an inverse matrix. This is Chapter 6. So the inverse of a matrix, in this case, since this is a 3 variable, to find the inverse of this kind of a matrix would take forever. So these inverse matrices will be given. First, we create the matrix equation. So that is a coefficient matrix multiplied by a variable matrix is equal to 750, one single column matrix. Now, in order to get this XYZ column matrix isolated, we need to get rid of this matrix. And that's where this inverse comes in. This matrix is the inverse of this. So if we multiply this matrix over here, so if we multiply this by the inverse, cancels it out, but then we have to multiply by the inverse here. So really what we need to show is this inverse multiplied by this. So the inverse multiplied by the column matrix 750. So the row and the column, we're going to have -21 and +10 times 0. That's -11. And here we're going to have -28 is 5. And then here we're going to have times 0. So -28 plus 5 is -23. And finally, we're going to have 7 plus 0 plus 0, which is 7. Question 14. We have a geometric series, and it's geometric because to go from 60 to 30 to 15 to 15 halves to 15 fourths, it's being multiplied by 1/2 every time. So, and then we subtract or add, subtract, add, subtract, add. So 60 times -1/2 is -30. -30 times -1/2 is +15. 15 times -1/2 is -15 halves. So the common ratio, R, is -1/2. Each term is multiplied by -1/2. So the explicit formula for the nth term of a geometric sequence, a sub n, is first term times the common ratio, the power of n minus 1. So a sub n equals first term 60 to the base of -1/2 to the power of n minus 1. So then that's part A. Nth term, a sub 10, is just using our explicit formula, plugging in the 10 for n. That'll be to raise to the 9th power. So this is -15 over 128. And then part C, does this infinite series, it's infinite because it's continuing to either add or subtract out to infinity. So it's an infinite sum. And in class, we talked about that there is a sum of an infinite geometric series as long as the common ratio, R, is a value that's between -1 or +1. So if the common ratio r is between -1 and +1, which in this case it is, then the infinite sum does exist. So for part C, yes, infinite series has a sum, and the sum of an infinite geometric series, if it exists, is first term divided by 1 minus r. So this is 60 divided by 3 halves, which is 40. Binomial expansion is from Unit 3, Chapter 7, Section 7.3. So rather than finding one particular term, we're going to expand the entire binomial. If it's raised to the fifth power, then part of what we need is all the coefficients of each term, which we're going to get from Pascal's triangle. We need the sixth row. So each term is going to be a product of coefficient, and then each of these terms raised to a certain power. So the first term of this expansion is going to have 1 as the coefficient. So 1 is the coefficient. And then first term is going to be raised to the fifth power. And then the second term, we're going to multiply also -4y, but it's raised to the 0 power. Because remember, the combination of these two exponents, this exponent plus this exponent, always has to equal the original exponent. Anything raised to the 0 power is 1. So we don't need that for the first term. The next term has a coefficient of 5, and this time 3x is raised to the fourth power, and -4y is to the first power. The next coefficient is 10, with 3x raised to the third power and -4y to the second power. The next coefficient is 10, with 3x second power, now -4y is to the third power. Next coefficient is 5, with 3x to the first power and -4y to the fourth power. And finally, we have 1 times -4y to the fifth power. Now here, 3x raised to the power of 5 is 3 to the fifth power. So 3 times 3 times 3 times 3 times 3, 3 multiplied by itself 5 times, so that's 243. X to the fifth. Now here, 3x raised to the fourth power. We've got 5 times 81 x to the fourth times -4y. So we need to multiply the 5 and the 81 and the -4. So that's -1620 x to the fourth times y to the first. Now for this term here, we have the 10, and then 3x to the third power is 27x cubed, and -4y squared is positive 16y to the second power. So we need to multiply the 10 now, and the 27, and the 16. That's going to give us positive 4,320 x to the third y squared. Now this term is going to be 10 times 3x to the second power is 9x squared. And then -4y cubed is -64y to the third. We have to multiply 10 times 9 times -64. And that's -5,760 x squared y to the third. Now this term is 5 times 3x times negative 4y to the fourth power is 256 y to the fourth. So we need to multiply. We need to multiply 5 times 3 times 256, which is 3,000, positive 3,840x as y to the fourth. And finally, negative 4 raised to the fifth power is negative 1,024 y to the fifth.